For centuries, humans have taken it for granted that they were in the most still and stable place in the entire universe. It seemed that everything in the sky moved: stars, planets, comets, the sun, but the Earth appeared perfectly motionless. Of course, we know today that this isn't the case. Even though we don't notice it, the Earth is moving, and quite a lot. In reality, there is nothing in the universe that can be said to be absolutely stationary. But, precisely, at what speed does the Earth move and relative to what? Let's try to understand it. Asking at what speed something moves by itself is a question that doesn't make much sense. What we really need to ask is, at what speed does something move relative to something else? In other words, we need to establish what in physics is called a reference frame. Nothing complicated, we know how it works. If we see a car speeding by while we're on the sidewalk, it will appear to have a certain speed, say 60 kilometers per hour. But if we're on a motorcycle moving at 50 kilometers per hour in the same direction as the car's speed will be only 10 kilometers per hour relative to the motorcycle. The sidewalk and the motorcycle are, in fact, two different reference frames. So, we need to understand the various movements of the Earth relative to the different reference frames we can choose in the universe. To begin with, let's keep in mind that the Earth rotates on its axis, which passes through the poles. This is the reason why we see the sun rise and set. From our reference frame, it is the sun that moves, but in reality, it is the Earth that spins like a top. As we know, the Earth completes a rotation on its axis in about 24 hours, and if we know the Earth's circumference, it isn't difficult to calculate the speed at which it is dragging us along. There's just one small complication. The rotational speed is maximum at the equator and becomes progressively smaller as you approach the poles. In fact, if you're exactly at the pole, you're just spinning on the spot. But if you go to the equator, Earth's rotation moves you at about 460 meters per second, or about 1,670 kilometers per hour. However, the Earth doesn't only rotate on its axis. It also orbits around the sun, completing an orbit in a year. The path is approximately circular, actually an ellipse, and the speed during this annual journey is about 30 kilometers per second. To give you a clearer idea, 30 kilometers per second is about 107,000 kilometers per hour. You heard right, 107,000 kilometers per hour. That's an incredible speed. It's much higher than that of most of the space probes we've ever built. Now, don't ask us in the comments why we don't notice that the Earth is moving so fast. Otherwise, you'd be reasoning like the ancients who, mistakenly, believed that the Earth was immobile. We don't notice it for the same reason we don't realize that a plane or a train is moving when we're inside, unless it accelerates or changes direction or speed. Galileo was the first to understand this. Reference frames moving at constant speed are indistinguishable from one another and are equivalent to a stationary frame. Yes, the Earth does change speed and direction, but it does so slowly that we can't perceive it. Experiments are needed to notice it. By the way, how do astronomers measure the speed of objects in the universe and thus our speed relative to them? The most commonly used method is to observe the frequency shift of light due to the Doppler effect. When a light source approaches us, its frequency increases, and when it moves away, it decreases. This applies not only to light but to any electromagnetic radiation. So, the frequency shift due to the Doppler effect can be used to very precisely measure the relative speed of a celestial object. Let's get back to Earth's speed. So, we are moving around the sun at an impressive speed, but that's not the end of the story. In fact, the sun itself is certainly not stationary. The sun is a star that is part of a larger system of stars, a galaxy, called the Milky Way, and the stars move within the Milky Way, and the sun is no exception. Naturally, the sun takes the Earth along with it, and so we and all the other planets in the solar system move with it. And how fast is the sun moving? Well, again, it depends on what you're measuring against. We know that the sun moves relative to the other stars in the galactic neighborhood at a speed of many tens of thousands of kilometers per hour. But in reality, in addition to moving relative to each other, all the stars in the galaxy's disk orbit around the center of the Milky Way. The Sun is about 27,000 light-years from the galactic center and completes a full orbit in about 250 million years. Imagine, since the Solar System has existed, we have completed only 18 galactic orbits. Well, anyway, due to this rotation, the Sun travels through the galaxy at about 885,000 kilometers per hour, and so the Earth moves relative to the Milky Way's reference frame at the same speed. But it's still not over, because our galaxy is moving relative to other galaxies. For example, we are moving towards the Andromeda Galaxy at over 400,000 kilometers per hour. But meanwhile, both we and the Andromeda Galaxy are moving together with many other galaxies in the direction of a great concentration of mass called the Great Attractor, at a speed, hold on tight, of over 2 million kilometers per hour. Okay, as you might have understood, in the universe everything moves relative to something else. It's not possible to establish a fixed reference frame. Moreover, when observing the motions of matter on increasingly large distance scales, we see that relative speeds tend to increase. However, these motions have nothing to do with the fact that the universe is expanding. Expansion concerns the dilation of space itself. It is not a motion within space, and so in that case, we can't properly talk about speed between galaxies. This is why, as I said in another video, there can be galaxies very far from us that are moving away faster than the speed of light, without this contradicting relativity. Well, anyway, the farthest thing we can observe, as we saw in another video, is the electromagnetic radiation that comes from the early stages of the universe's history when matter was extremely hot and spread throughout space. We said that we are completely surrounded by this radiation that reaches us from every direction and is called the cosmic microwave background radiation. In a sense, the reference frame of the cosmic microwave background is the most extensive we can consider, as it covers practically the entire observable universe. In other words, all of space is pervaded by this extremely uniform sea of photons left over from the origin of the universe. And since the universe is expanding, the density and temperature of this sea of photons decrease over time. So, we can choose as a reference frame the one in which the cosmic microwave background has the same density and temperature at every point in space. Incidentally, this is also the reference frame in which galaxies should be stationary if there were only the expansion of the universe. But in reality, there are all these other motions due to differences in density from one point to another in space, and we can measure these motions precisely relative to the frame in which the cosmic microwave background is uniform. Of course, the cosmic microwave background is not an absolute reference frame, which cannot exist, but it is a useful reference frame in which the model we use to describe the universe takes a very simple form. It is a sort of global or average reference of the universe. And so, we can ask, at what speed is the Earth moving relative to the cosmic microwave background? In practice, due to the Doppler effect, when observing the cosmic microwave background in the direction of Earth's motion, we see it with a higher frequency, while in the opposite direction, the frequency is lower. An equivalent, somewhat simpler way to say the same thing is that the cosmic microwave background appears a bit warmer in the direction of motion and a bit cooler behind us. Naturally, the speed changes slightly throughout the year because the Earth orbits the Sun. However, the result is that the Earth moves relative to this global reference frame at a speed of about 370 kilometers per second, or about 1,332,000 kilometers per hour. Thanks for following us with this video. Leave a like to support us and subscribe to the channel.